All right, 12.1, Intro to Kinetics. And for the worksheet, just do all of it. This is going to be a fun chapter, okay? I like this stuff. And there's a good bit of math in this chapter, but I think you're going to find this, as we were returning to math, you'll find this to be one of the easier math chapters. In fact, kinetics is pretty easy, the math, believe it or not, when it comes down to it in the end. And the chapter after it, the chapter after it, equilibrium, also. It'll just get to be a little bit crazy. We're in chapter 12, 13. Chapter 14, 15, around there, it'll get a little bit of craziness that you'll see involved. Okay, so chemical kinetics. In the beginning of the notes here, I wrote down just the definition. Stoichiometry, anytime you take an equation and you talk about, all right, well, let's just say, for example, H2 plus O2 to give you water. Stoichiometry is concerned with mole to mole, gram to gram, making predictions like if I have this much, how much will I produce, those kind of things. The study of the quantitative relationships between reactants and products in the chemical change or chemical reaction. Change from product to reactants. What are the volume here, volume there, mass here for gases, what's the pressure here? All of that's involved anytime I'm using the equation to predict. All right? Thermodynamics is a study of the heat that is involved, or energy changes from beginning to the end. Like basically we'll say delta H, delta G, delta S. It says the study of energy and its interconversions. Heat is it exothermic, endothermic, and of course, is it what is the entropy positive or negative? Is it Gibbs free energy positive, negative? That's going to come back later on, but not in this chapter. Chemical kinetics is a study of chemical reaction rates. How fast does a chemical reaction occur? Now, in measuring a rate, there's an equation given here. It says NO2 plus CO gives you NO plus CO2, gas. These are all gases, gas. Okay, now, one way to think about this, it talks about three factors, just more than just three factors. Actually, I have my other notes as well that was from the UCLA notes. I don't know if anybody went to that program and saw that earlier. But what are all the factors that can influence the reaction rate? Well, I'll mention, let me see. I didn't exactly put all of these on here. Some of these we're going to get to later in the chapter, but I'll go with the ones in the notes first. First of all, it talks about collisions. In order for NO2 and CO to react and form these, there has to be a collision involved. Now, what the actual collisions are, that's a different study. It's called mechanism. So it won't always be so easy as I might make it look here. But let's just say you had a molecule of NO, and just say that it was going to bump into CO to make CO2. Well, think about this. If it bumped into a CO, carbon monoxide molecule like this, yeah, you could make a CO2. It could bump into it. But first of all, you got to bump. These have to be sufficient energy so that these will break apart and these will stick together. So you can see you can get CO2 pulled off in NO. That would make sense. But what if the molecule collided like this? What if the C were to hit the NO? Well, that would not be an effective collision, okay? Or what if the O on a carbon hit the O? That would not be an effective collision either. So that would not work. That collision would not work. In fact, when you think about it, probably at least half or most of the orientations they would hit in would not work. You have to hit right on with the O and the CO. So that's actually number two. The orientation of the collision matters. One is the energy of the collision. It has to be enough so that it will it can break the old bonds, and it can also it can form a new bond. Now it could just be that they bump into each other and they just move. Like, gas molecules are always bumping into each other. So they got to have the correct amount of energy. By the way, we'll talk about it later on, and I think we've mentioned it before. The word activation energy. That's the minimal energy needed in order for the molecules to collide effectively if they're in the right position. But activation energy is the energy that needs to be added in order for the reaction to occur. Okay. Now, the last one on there is frequency of collisions. So, you know, if there are more collisions, it's more likely to react. So if I have a big tank, a big container, and let's just say I have in here all these molecules. I'll use the white little ones here. Actually, I might even use this to explain a different concept as well. And let's just say that we have the yellow. Okay. Well, first of all, the white and the yellow can bump. That isn't really too different, does it? Well, the yellow and the white ones could bump together and nothing could happen. All right, they could bounce off of each other. All right, or they might bump into each other and boom, make a new compound. Okay, so if we heat the temperature up at a higher temperature, there could be more collisions. Would you expect there to be a faster rate of reaction or slower? You would say if the temperature is increased, it'll be a higher reaction rate. They'll be reacting faster. What if I took away a whole lot of molecules? Like if I took away, they only had like 4 yellow molecules and 5, not even that. That would have messed. Only 3 yellow molecules in this giant container, and maybe 3 or 4 and 3. Well, that's going to be also a slow rate. So the concentration also matters. All right. Well, anyway, we're going to kind of get into it. A lot of it makes sense, and you'll see. I'm going to get back to it later on. Well, I better say it now, though. So one thing I better tell you: temperature will affect it. It's not in the notes, is it? But higher temperature. Actually, higher temperature means average kinetic energy. That's number one. Higher temp means faster rate. The rate goes up. Okay. If you have a higher temperature, if you have a higher concentration, that means you're going to have a faster rate. Low concentration lowers the rate. Let's see. Is there anything else in there? Orientation, frequency. A higher collision frequency. And of course, collision frequency can happen because of the temperature, or it could also happen if, say I had a big container like this, all right, and they're moving around. Well, if I were to have a piston and I were to bring this down and compress this into a smaller container, now it's going to have a smaller volume, compressed, and so now you're going to have more frequent collisions as well. So that's good, higher frequency. That will raise the frequency as well. Higher frequency, higher rate. Okay, then these are some other notes I'm looking at. The physical state of the chemicals matters as well. And I'll tell you, what do you think is going to be easier to react? A gas, a solid, or a liquid? And the solid, liquid, gas. The easiest to react will be the gas. Think about it. If one of these were a solid, say you've got a gas inside here, and they have to react with this block, this metal block, like to make like iron oxide, iron and oxygen. Let's just say, well, oxygen would be diatomic. To make iron oxide. Okay, it's going to be kind of tough for that to react. It will happen, but it's mainly going to happen just on the surface all around that. All right. So, but it'll be a slower rate. On the other hand, if I were to grind up all of this, well, you'd have to use some good machinery to do that, and make iron dust. Iron dust, that increases the surface area. In fact, that's another factor. Having high surface area for a solid, well, for anything really, but solid or liquid, higher surface area increases the rate. Or just being in, as we said, that actually counts as surface area. A solid, like dust. Okay. Oh, I thought I was going to sneeze. Look away. It's good to get all the dust on here. If I had, instead of iron solid or iron dust, if I had iron gas, iron vapor, well, now it's going to be even easier to react because now the molecules can bump right in. They can form iron oxides, all that kind of stuff. So, surface area. Let's see what else I talked about. Concentration, I talked about. The pressure, I kind of talked about that a moment ago. If it's a gas, if you have a high pressure, you'll have a higher rate. And I kind of showed you that with this one as well. If you increase this, because it's going to make more collisions. I guess I wrote down it's going to increase the collision frequency. You might remember that pressure and collision frequency are directly related to each other. Physical state reactants, and then something called a catalyst, which I did not put on there. Okay, all right, so I wanted this first intro those little factors, and you'll find them if you read through your book. But there's even more. When it gets to the math of this, there are some strange things here. Interesting things going on. I'll show you. Okay. On your notes, you have, I wrote down, well, actually 12.1. It's actually 12.2 now. And it's the same reaction, NO plus CO to give you, oh no, it's not the same reaction. I am sorry. It's NO. In 12.2, if you blow your notes up, you can look at this one right here, this chart. 2NO, nitrogen dioxide gas. They bump into each other. They collide. You can put NO2 plus NO2. Gives you 2 nitrogen monoxide plus oxygen gas. And what they're doing is they're showing you some data. As time goes by, they're showing you what happens to these things. Now, the first one talks about the time in seconds. It's way over here on the end. And you see, you can't read the number 2 good, but it's 0, 50, 100, 150, 200, 250 seconds. But then it talks about the concentrations. And they give you 3 columns, The NO2 concentration. And remember, the correct way to do that is with brackets. The nitrogen monoxide concentration. And the O2 concentration. By the way, I need to add this in. Concentration is molarity. And you might think about that. Normally when you think about molarity, you think, well, moles of solute per liter of solution. Well, molarity can also be used for gases to represent and to talk about what the concentration of gases is. If I know molarity is mole per liter, that's the concentration. Molarity. Okay, M, whatever. M, concentration, molarity, those all mean the same. It's always mole divided by liter. Okay, so if I know how many moles of gas I have, and I know the volume of the container, mole divided by liter, that is the molarity. That's called the concentration. You're going to see that used in this chapter and in the next chapters as well, especially chapter 12 and chapter 13. So you're going to get used to seeing that. Concentration, concentration, concentration. So look at what happens as time goes by to these things that you see here. It says that NO2, look on the very first at time 0. I won't write them all down, but at time 0, it's 0.0100 for NO2. You have no NO and no NO2. By the way, let me tell you something interesting about this reaction. If I had a tank, like maybe it was a glass container, sealed glass cylinder. Well, nitrogen dioxide is reddish brown, the color. I should be able to show you that, I hope, at some point. Nitrogen monoxide is colorless, has no color, and of course oxygen is colorless too. No has no color. No color, okay? But NO2 does have color, reddish brown. So, if you think about it, I want to say reddish, brownish, orangish. I don't know if I can kind of make it with my chalk, but I want to show you. When you start off, the gas kind of has this color. Maybe I can do it this way if I put together these colors. Yeah, that might look good. Orange and red kind of together. So it starts out that the whole tank looks like that. You only have gas, NO2, put inside it. Because really this reaction, when you put 2 NO2, it really means, here's the reaction. NO2 plus NO2 gives you that. So the NO2s have to bounce into each other. They bump, nothing happens, boom, now some react. All right, boom, 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 no, yes, and some react. As time goes by, this will react to give you this stuff, okay? Not every collision is going to be a reaction, but the ones that are effective with enough energy will. So instead of writing NO2, I'll put 2, but 2 NOs are bumping into each other. All right, so it starts out looking this color. What's going to happen as time goes by? Sometimes they can tell you data like this on an AP. This doesn't even really take a lot of, it doesn't take any math, or not too much thinking to figure out, oh, it's going to get lighter and lighter and lighter. As time goes by, the color, is it getting lighter? It's getting on my hand, I guess. But as time, oh, now it will. As time goes by, the color gets lighter and lighter and lighter and lighter. Okay, and so you'll know the reaction's occurring. What is that? Why is it getting lighter? This one is going down. This reactant, R for reactant, and these are products, okay? Now notice these numbers on your notes there on the chart. 0.0100, 0.0079, 0.0065, 0.0055. Okay, so we got the idea. We don't have to write all these down. But look at the NO, what it's doing. Well, it should be going up, right? So it goes from O to 0021, 35, 45, and oxygen goes 0011, 0018, 0023. So this is increasing, and that one's decreasing. All right, that makes sense. Well, AP Chemica, they love to show you graphs, and so let's look at a graph here. And you see one on the paper. Oh, actually, I've got it. Yeah, it doesn't, it's a little bit hard to see the numbers on that graph, but I'm going to just tell you what's going on there, and I'll just point to it and show you. But one of the curves on this side, you have concentration. That means the molarity of the chemical. And down here, you have time as time goes by. Now, we start off with NO2, and initially, if I look on the paper, it was 0.0100 molar. But at time 0, it was 0.0100. Yeah, molar, mole per liter. So we'll just put a number up here. It doesn't really matter. As time goes by, it decreases like that. You see a curve going down on your paper, okay? I mean, it's kind of hard to see it, but there it is, that little curve. You might be able to blow it up on your computer if you can see better. That one's going down. Then you see there's also another graph that's coming up. And it looks almost like the mirror image of it. Then you see another one coming up, like right here, that's goes a little bit lower. Oh, there's a lot to tell you about these graphs, okay? The first thing I want to tell you about the graph, well, first I'm going to tell you the obvious. This one decreases, so what would that have to be? I already told you when I drew it. That would have to be NO2 molarity. As time goes by, it decreases. Okay, so these two are increasing. At the beginning, there was none of this. It was only red-brown gas. But as time goes by, they bumped into each other. They made this. It became colorless. So these things started out at 0 and they increased. Okay, which one of these do you think is NO2 and which one is O2? Well, here's a fun thing to look at. Guess what? The amount of moles of this to this, 2 to 2 ratio and 2 to 1 ratio, the graph will exactly match the stoichiometry. So in other words, the graph, since it's 2 to 2, this graph will look just like that one, but it will be a mirror, a reverse image of it. So that'll be NO gas. The oxygen will increase to only half the rate that the NO will. So it'll at only half the rate. Sorry, or half the final volume. So whatever this goes to, we can't read all the numbers in there on the graph too well. But for example, if that had been 4, then that would be 2. It went halfway. All right, and that would also be 4 going down, negative. From 4 down to 0 or 5 down to 1, whatever. If that changed by 4 parts, that goes up by 4 parts, and that goes up by 2 parts. That's one thing to look at. It matches stoichiometry. The other thing that's important to look at is that when it increases, you see, you're getting a graph here. You're not getting, you're getting a curve and not a line. Like, look at just only the NO2 for a second. Actually, I can kind of use the color that it has. When I bring it down, it goes like that. It doesn't do this. It's a curve. What does that mean? That means that it's decreasing exponentially. Now, I know that word might kind of think, oh no, what does that mean? Yeah, log and all that. Yeah, that's going to come up later on in this chapter in the math. But let me just explain what it means when something decreases exponentially. When it does, what's happening is the rate is changing every moment. The rate, like, instead of being a straight line, if I draw a straight line there, if I drew what's called a line tangent, I get a line like that. But down here, to the orange, the line tangent looks like this, and here is pretty much flat. So the slope is decreasing. Whatever the slope does is what the rate is doing. Remember that. Whatever the slope does, the rate is doing. So on a curve, we don't really talk about slopes very much, but if I take 3 points on that curve, and I look and say, okay, here the slope is really inclined, I could calculate that at that point if I want to take, change in y or change in x at that point, do the same at that point or the same at that point. But I noticed the slope is going less and less inclined. It's getting, here's a real high slope, will be a high rate. It's decreasing really fast, decreasing slower, and decreasing very slow. Even this way it works. The tangent line to this is really steep here. At first, the chemical is formed at a high slope, high rate. It's at a lower rate, lower rate. Notice the slope. The slope of the line is decreasing for all of them. Okay? So that's an interesting thing to look at as well. Why does that happen? Well, one way you can look at it, and I kind of told you this before, it's the same thing I kind of showed you. So say I've got these molecules all, I'll just use this color instead. So let's just say that if they bump in effectively, they'll make an orange and a white one together. So right now, let's just say you wait, okay, ready, set, go. You wait for 1 minute. Okay, after 1 minute, boom, 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 some bounce, bounce. Okay, boom, that one formed. And that one formed. Okay, uh-oh. I erased the wrong one. That one formed, that one formed. Okay, now, that was 1 minute. Well, let's make it 3. Boom, boom, boom. So 3 of them formed in 1 minute. Okay, so that one is reacted, finished. That one is reacted, finished. That one's reacted, finished. Now, in the next minute that passes, so that happened in the very beginning. Like we'll say immediately, boom, 3 of them reacted. But now, a slower rate, a little bit later, less are going to react. Can you see why less are going to react? Look, now, not only do you have, sometimes they bump into each other and nothing happens. But now, they could bump into a molecule that's already reacted and nothing will happen. So now you got obstacles in the way. And you have less molecules, a lower concentration of molecules to react anyway. So every time you take some out of the picture, they're still in there. I mean, their reaction is done, but now it makes it harder. And so the next, minute number 1, 3 reacted. Minute number 2, maybe only 2 are going to react. Like that one might form there and that one might form there. And then the last minute, there's only 1 left anyway, that and then that won't react. So that tells you that's going on as time goes by. All right. So it is an exponential change on that. Now, I talked about this a moment ago, but I'm going to bring it up again here and show you in this term. You're going to see this on one of your worksheets as well. That if this is concentration of whatever, chemical A over time, versus time, and your graph looks like that. Okay, first of all, the initial rate, what is meant by the term initial rate? And let me see if this is on your worksheet. It is, what we do, you get to skip to the next page, okay? Actually, we're going to skip this section and go all the way down to here before the math comes up. But down to this little section. Look at this little graph here. I'll just talk about this first. And I might have to do the math on a separate video, but we'll see. It says points A, B, and C represent concentration of reactant A at 0, 1, and 2 seconds. So 0, 1, 2 seconds. And we have A, B, C. So A should be a little bit off the line, okay? Then B, and then C will be over here maybe. Okay, and it says label the graph to identify instantaneous, average, and initial rate and define each. Okay, initial rate, well, when you start a chemical reaction, obviously at time 0, nothing's happened yet. You start ready, set, go, and maybe you have to heat this up a little bit or whatever you do to start the reaction. the initial rate, when you first decide to measure something happening, or if you have sometimes there's a color change, and you can detect a change in the color. But as soon as you decide to measure, okay, I'm going to measure how much NO2 reacted after 10 seconds or whatever, boom. All right, so you wait till 10 seconds. All right, when I get the new molarity after 10 seconds, that the initial rate would be the slope at that point. All right, from where I started to there. So initial rate would be the slope of the line tangent to the curve at that point. That's your initial rate. Not really that big of a deal. Now, initial rate. Instantaneous means that would also be an instantaneous rate. It's the rate at any given moment, and it's always the slope of the line tangent to the curve at that time. That would be the rate. This divided by that. The initial rate would be, it's the slope of the line. Just say at point A, technically it would be, I started at time, my initial point was 0, 0. 0, well, not 0, 0, because your concentration wasn't 0, but you start with your initial XY and then go to A. That would be your initial rate. Yeah, that's what I'm trying to say. It wouldn't have to be that. The instantaneous rate would be the slope of the line at that point. Initial rate would be from the beginning 0 point to that point. I should say the slope of that. That's your initial rate. That's the first point you're going to get on the graph, actually. So yeah, it is an instantaneous rate, actually, that you just get across. And you might decide to let it be 10 minutes before you get that point, and it might be down here, but oh well. But the initial rate would be the change in concentration divided by change in time. Remember, slope is change in y over change in x. So the change in A, the concentration of a chemical, forget that A, divided by the change in time. That would be your initial rate. Instantaneous rate, as I just said a moment ago, is the slope that is of the line tangent to the curve at any point on the curve. So at time for the B, at time whatever this is, at time number 1, the instantaneous rate would be the slope of the line tangent to point B. At time 2, if I draw a line tangent to C, to the point C, tangent to the curve at point C, the slope of that line would be the instantaneous rate at C. All right, and then average rate, like if I said I had to pick 2 times, from time A to time C, the average rate would be the slope of the line from A to C. So this is kind of technical. You're not going to hear a lot about that. I think the most important thing to know is, out of this is, if I take the slope of a line tangent to the curve, that will be the rate, the instantaneous rate at that point. Okay, now, do I have time to show you a little bit of the math here? I think I'm gonna wait a second video to get into the math for it, because I have one more thing I got to do right now. But this is the non-math, and you'll find the math easy on this first section, and then it'll get a little bit crazier, but it'll be fun. You'll like this chapter. I'll see you guys, and there'll be a part 2 in just a moment. All right.